going to be talking about nuclear chemistry. And nuclear chemistry is a really interesting aspect of chemistry overall. It gets into some things that are very different from what we've talked about before. So I look forward to going through this with you, and hopefully you will enjoy it as much as I do. So we're going to just get a couple of things, some terminology taken care of right off the bat, which is about isotopes. We have this designation that we use for isotopes, and I'm sure you guys remember the number on the bottom indicates the atomic number, and the number on the top is the mass number. Well, we want to introduce a couple of new terms. Nucleons are just protons and neutrons. So the mass number indicates the total number of nucleons. In this case, there are 6 protons and 6 neutrons and carbon-12. And so the nucleons is going to be equal to that mass number. The isotope, an isotope is an atom with a particular number of protons and neutrons. And a nuclide is a nucleus of a particular isotope. And as I mentioned a minute ago, the number on the bottom is the atomic number, which we usually give the designation Z. And the number up on top is the mass number, which we will give the number A. So just real quick, just to make sure that you guys are on the same page, this is stuff we did way back in chapter 2. But how many neutrons are in this? So to get the answer, we simply subtract the number of protons, the atomic number, from the mass number. So 41 minus 19 will give us 22 neutrons. All right, for vanadium 50, we'll do 50 minus 23, and that will give us 27 neutrons. And then for sulfur, we've got sulfur 36. So 36 minus 16, that gives us 20 neutrons. So we want to look at number 7 on the in-class assignment. So I'll switch over to number 7 here. And this is really, really easy, provided that we've got a periodic table available. So I have my trusty periodic table here ready to go. Manganese 55, and you'll see that the atomic number is not given on here, so we'll have to look and see where manganese is. There's manganese at 25, so the number of protons is 25 protons. For the number of neutrons, it'll be 55 minus 25. If you're not feeling very confident, you can break out your calculator, but that's 30. All right, so here we've got mercury 201, so Hg 201. Well, here's mercury, element 80, so there are 80 protons. And then 201 minus 80 gives us 121 neutrons. All right, and then finally here we've got potassium. Well, the element potassium is K, so 39, so that's potassium 39 if we wanted to write it in the same designation. And then, so the number of protons, well, we'll look for potassium here. Potassium is element number 19. So we've got 19 protons, and then 39 minus 19 gives us 20 neutrons. Okay, so that's hardly a problem. You wish you had a whole test full of those, but you're not going to have a whole test full of those. So now let's really get started on this chapter. We're going to be talking about radioactive decay and the different modes of radioactive decay. First of all, radionuclides, those are just radionuclei that spontaneously decay into new particles. And we will find that there are several different modes that this can occur by. Alpha decay, beta decay, and beta minus means beta decay. If it says beta plus, that will mean positron emission. In this textbook, it uses just beta to mean beta decay, and it does not use beta plus to indicate positron emission. It just says positron emission. So we'll talk about that here in a minute. But in most textbooks, beta plus is positron emission. EC is electron capture. Gamma decay is gamma radiation. And then N decay, that's neutron decay. And then P decay, that is proton decay. So we're going to talk about each of those here shortly. over here is a graph, and we're going to discuss this graph in a lot more detail coming up, but it is a way of analyzing what's going to happen when you have each of these types of decay. What's going to happen to the atomic number and what is going to happen to the neutron number. So we're going to refer back to this same image here in just a little bit. So we're going to start with alpha decay. Oh, before we start with alpha decay, we're going to talk about how it is that we measure radioactivity, how it is that we measure these decays. Well, we need to have something like a Geiger counter, and I do not have a Geiger counter with me because I am currently sheltering in place at my own home, and I do not have access to our school's Geiger counters. But hopefully in the future I can fix that and update the video. But for now, we will say a Geiger counter is just a way of measuring our activity in a radioactive sample. So here there's just a counter, a cathode, and an anode. There is a window on the front of this tube, and inside the tube there is argon gas. Whenever some type of ionizing radiation enters that tube, that causes the argon gas to get ionized, and that allows an electron to move from the cathode to the anode. So every time there's a bit of ionizing radiation, we are able to get a count on our counter. And so if it's not ionizing radiation, we won't detect it, but if there is ionizing radiation, we can detect it. So that is how that works. Usually I would get it out and show everybody how our particular radiation detector works. It's a little bit different than your typical Geiger counter, but in any case, it is what it is. All right, so here we want to look at alpha decay. And in alpha decay, that is the process by which an alpha particle is emitted from the nucleus of a radioisotope. An alpha particle is simply a helium nucleus. So here we've got uranium-238, which is the most abundant isotope of uranium. And uranium-238 undergoes alpha decay, and when it does, we get thorium-234 plus the alpha particle. Since an alpha particle is a helium nucleus, we can write it like this. And this is typically how we will write it when we do these processes. So one note, the atomic numbers, which are the numbers along the bottom, they have to add up on each side. So 92 is equal to 90 plus 2. And the mass numbers also have to add up. So the numbers along the top, 238 is 234 plus 4. And if those numbers don't add up, then something is wrong. Here is another example of alpha decay. So the substance americium and americium-241. And I just realized there's a typo here. That should be neptunium. Neptunium is element 93, not 92. But there you go. I just emphasized the importance of doing that. In any case, we will be doing. Normally, we would be doing a demo of an alpha emitter. So just hold on a sec. And there I fixed it, so now it says the correct atomic number. Hopefully that will be fixed before you download that. All right. Again, the whole point of this is that we do get alpha decay. We also get gamma radiation, which we will be talking about here shortly. Normally, the alpha emitter I have is americium-241, which is actually a small sample that comes from inside of a smoke detector. The way that it works is that there's a little chamber with the ionizing radiation, that americium-241. It's a very small amount, so not very dangerous. And it ionizes the air inside of that chamber. And if smoke, and then it measures the conductivity across these two metal plates. And if smoke gets in there, it changes the conductivity, and that allows the smoke detector to detect the radiation, or it allows the smoke detector to detect the smoke. So unfortunately, it also allows the smoke detector to detect steam and any number of other things. But hey, it's not perfect. Next, we want to look at beta decay. Beta decay, it's a beta particle, and a beta particle is an electron, and it is emitted from the nucleus of a radioisotope. So I'm going to say that again. A beta particle is an electron that is emitted from the nucleus of a radioisotope. And if you've been paying attention throughout chemistry, that's not normally where we keep our electrons. Normally, we keep our electrons out in the orbitals, not in the nucleus. Well, so this is unusual. So what in essence is happening is one of the neutrons in your one of the neutrons in your atom is getting converted into a proton. And so we'll see that the mass number stays the same, but the atomic number goes up. And that's because it is emitting a beta particle. And this is the way we can designate a beta particle, 0, -1 beta. However, we can also just put the designation for an electron. And that designation for electron is just to use the letter E in place of the beta. So that is an example of beta decay. And then another example of beta decay is strontium-90. Strontium-90 will undergo beta decay to give us yttrium-90 and the beta particle. And again, you'll see 90 equals 90 plus 0, and 38 is equal to 39 plus -1. Again, normally I would have a beta emitter and I would show you how it worked on our radiation detector, but I do not have that with me today. All right, positron emission. So for positron emission, in positron emission, we get, so in positron decay, a positron, or it's a beta plus particle, is how it's indicated in most textbooks, is emitted from the nucleus of a radioisotope. Positrons are the antiparticle of electrons. So positrons are the antiparticles of electrons. What that means is if a positron runs into an electron, the positron and the electron will completely annihilate each other and create two gamma rays. And we're going to talk about that here in just a little bit, but pretty cool. All right, so here is a positron emitter, carbon 11. And again, you'll notice the numbers on top. 11 is equal to 11 plus 0, and 6 is equal to 5 plus 1. All right, and there is our positron. And then here is an example of another positron emitter, magnesium-23. It undergoes decay and gives us sodium-23 plus a positron. Now, even if I had my radiation detector, I could not show you a positron emitter because it is too dangerous just to have like sitting around. Even like in a lab, you would need it in a secure area. All right, our next one is electron capture. In electron capture, we'll find that an orbital electron is captured by the nucleus of an unstable isotope. And then electron capture has pretty much the same result as positron emission, where it converts a proton into a neutron. If you recall, in beta decay, we converted a neutron into a proton, but in positron emission and electron capture, we convert a proton into a neutron. So here we've got rubidium, rubidium-81, plus the orbital electron. It absorbs that orbital electron, and we get krypton-81. And that is an example of an electron capture. Here we've got iron-55. It absorbs an orbital electron, and we end up getting manganese-55. And just like with the positron emitter, I do not have any electron capture demos. Not safe to have for demo purposes. Next, we'll look at gamma radiation. And gamma radiation is something that's a little bit more familiar because it is electromagnetic radiation, so it is something that you guys have heard of. Gamma radiation usually comes about, it usually occurs, it accompanies some other type of radiation, as the radiation lost when nucleons rearrange themselves into a more stable arrangement. So that is gamma radiation. So you can get gamma radiation one way is if you, and I mentioned this one a little bit earlier, if you have a positron plus an electron, they will annihilate each other and give us two gamma rays. So the positron and the electron, they both have mass, and the gamma radiation does not have mass. And you might think, is that a violation of the law of conservation of mass? And I will say, no. However, something interesting happens, and I will talk about that in a bit. Here is an example where gamma radiation is given off. This is a fission reaction. We'll talk about fission later in the chapter in a lot more detail, but in this fission reaction, uranium-235 is hit with a neutron. We get barium-141, krypton-92, 3 neutrons, and a gamma ray. So gamma radiation is one of the components of that is given off. Again, you'll notice that 235 plus 1, that's 236, and that is equal to 141 plus 92 plus 3. And that will give us the, that will give us the 236. And then the number on bottom, 92, is equal to 56 plus 36. And cobalt 60 is an example of a gamma emitter. When it decays, it gives us nickel 60 plus a beta particle plus gamma radiation. So the beta particle, there's kind of no way around it on this one. It does give off that beta decay. So that is an example of a gamma emitter. All right, neutron emission. This one is very rare. Neutron emission, there's just too many neutrons in the nucleus, and the neutron is just lost from the nucleus. It's very rare and very fast. So if you form one of these nuclei, like helium-5, it will not stick around very long, and you'll get helium-4 plus a neutron. All right, and here beryllium-13, it will undergo neutron decay to give us beryllium-12. Well, it turns out beryllium-12 is still radioactive. It goes on and gives you something else. But the neutron, these neutrons can't be detected by a normal Geiger counter because these are not ionizing radiation. Now, just as a word of caution, that does not mean that they are not dangerous. They are indeed quite dangerous. But they do not count as ionizing radiation. All right, and then finally, we've got proton emission, and proton emission, again, is quite rare, and that's just where a hydrogen nucleus is lost from an unstable nucleus. Typically, this is when we have way, way too few neutrons, and so here we've got cobalt-48, which is a very unusual isotope for cobalt. It gives off a proton, so it gives off a mass number of 1 and an atomic number of 1, so you'll see both of the numbers go down by 1, and then here we can also write it like this, where we get where we can write hydrogen. It's just the nucleus of a hydrogen. So now we want to look at number 11 on the in-class assignment. So I'm going to switch over to the in-class assignment. We'll scoot down here. Okay. So the easiest way to go about doing this, to setting up these problems, is simply to just do the math. So 7 plus 0 is 7, and 4 plus -1 is 3. And if we look on our periodic table, element 3 is lithium. So we'll get lithium. All right, and if you see here, this is, so we've got 7, so 7 plus 0 is 7, then 4, -1, and that's going to give us lithium, all right? And that is going to be electron capture. You'll see in some textbooks it is called K capture. Okay, so next we've got, let's see, 254 is equal to 4 plus 250. And then 100 is equal to 2 plus 98. And element 98, if we look at our periodic table, it's down here. There's element 98, and that is californium. Oh, there it is, californium. So element 98 is californium. CF. That, as you can tell, that is alpha decay. All right, next we've got 32 is equal to 0 plus 32, and 15 is equal to negative 1 plus 16. And element 16, as we can see, is sulfur. And if that is, if we've got a negative 1, that means that that was beta decay. So that is beta decay. All right, 13 is equal to 13 plus 0, and 7 is equal to 6 plus 1. And that 1, that has to be a positron, and so this is positron emission. All right, next we've got 239 is equal to 235 plus 4. And 94 is equal to 92 plus 2. And that is a helium nucleus, and of course that is alpha decay. So that is alpha decay. All right. So when it comes to the patterns of nuclear stability, we want to look at that next. With our patterns of nuclear stability, we will find that any atom with more than one proton, so anything but hydrogen, has these repulsive forces that are caused by those protons being together. So like anything from helium on up, well, protons are positively charged and they are going to repel each other. So in order to keep those protons stuck together in the nucleus, we need some really strong force, and we actually call it the strong nuclear force. That strong nuclear force holds those protons together. Well, the thing that helps to facilitate the strong nuclear force is the presence of neutrons. But you have to have the right number of neutrons. You can't just have any number of neutrons in there. You've got to have the right number. So we're going to look at what kinds of patterns show up for these neutrons. So we're going to start here. We've got this diagram over here, but I want to talk about the diagram that is over here on the right first. So you'll notice along the x-axis we've got the number of protons, that's the atomic number, and on the y-axis we've got the number of neutrons, which we can call the neutron number. Every one of these dots that are on this particular graph represents a known isotope. Some are radioactive and some are stable. The ones that are radioactive have a yellow color to them. They're a yellow dot. And the ones that are stable are the dark ones, the black dots. So those are the stable isotopes that are known. And those stable isotopes, it turns out there are 265 of the stable isotopes that are known. And so here's what we know about those stable isotopes. It takes approximately, for smaller elements, it takes approximately 1 neutron for every proton to have a stable isotope. And you'll see this red line represents the 1-to-1 neutron to proton ratio, and we'll find down here for the smaller isotopes, it's about 1 neutron for every proton. However, as the atoms get bigger, it requires more glue, more of those neutrons to hold the nucleus together. So we'll find that by the time we get to iron, it's about you have to have about 15% more neutrons than you have protons. By the time we get to iodine, it's about 40% more neutrons than we have protons. And then finally, by the time we get to bismuth, it's about 50% more neutrons than we have protons. So there is a range of values that are possible, and sometimes you'll have numbers in between, like you'll have 2 numbers that are possible, but the one in between isn't. And so there's some weird stuff that's going on here. So what we're going to find is that when we have one of the yellow dots, to get to a stable isotope, it's going to do one of these types of decays. And one of those types of decays will get it closer to being a stable isotope. So for example, if it's above, it's more likely to do beta decay. So we'll more likely lose an electron from the nucleus. If it's below, we're more likely to do electron capture or positron emission, and it will go up and to the left. So the atomic number will decrease by 1 and the neutron number will increase by 1. If we've got relatively large elements, the ones that are out here, for example, uranium, they are more likely to undergo alpha decay. So I've got a special version of this chart that demonstrates this. It's color coded, and it represents what is going on. So again, all the black dots represent the stable isotopes. The blue dots represent elements that are more likely to undergo beta decay. Now, it doesn't exclude the possibility that other reactions could occur, but it's more likely to undergo beta decay. So these things will likely undergo beta decay to get closer to a stable nucleus. The ones that are orange are more likely to undergo beta plus, which is positron emission. And anything that's likely to undergo positron emission is also likely to undergo electron capture. Those kind of go together. We'll find for alpha, these are the yellow ones that are up here. Those typically are the ones larger than bismuth. Our largest stable isotope, we're going to go back. Our largest stable isotope is bismuth 209, and it has an atomic number 83. Well, all of the elements that are larger than 83 are radioactive. And so anything greater than 83, we're going to predict it's going to undergo alpha decay. Now you'll see there's a couple of other ones here, the green ones, and there's just a couple of them. Those undergo spontaneous fission. Usually what happens is you form them very quickly and then they undergo fission. So those are unusual. The red ones are along here, along the edge, and they have so few neutrons that they just spontaneously give up a proton. So they do proton decay. The ones that are purple here along this, there's not very many of them, and they undergo neutron decay. And as I mentioned, all of the black ones are stable isotopes. And then anything that is white is an unknown, it's an unknown isotope. They either haven't found it, haven't studied it, whatever. So next thing we want to do, I want to mention about these numbers. So 6, 14, 28, 50, 82. You remember way back when we studied, what did we study? We studied electron configurations way back in chapter 6. In electron configurations, we had certain numbers of electrons that would fit into each shell. Well, it turns out in the nucleus, we have a similar thing where there are shells. For lack of a better term, we'll call them shells. And it turns out that certain numbers of protons and neutrons are more likely to give us stable shells. And those numbers are sometimes called magic numbers, but there's nothing magical about them. They're just configurations that tend to be stable. And that's when we have either 6, 14, 8, 28, 50, or 82 protons. We'll find that there are more isotopes of those particular elements, or 6, 14, 28, 50, 82, or 126 neutrons. Those tend to be more stable as well. Just as an example, element 50 is the element tin. Tin has 10 stable isotopes, so you'll see there's a lot of black dots there right in a row for tin. Let's see, 82 here going across, 82 neutrons. You'll see there's quite a few stable isotopes, or quite a few elements that have 82 neutrons in them. So that is kind of interesting. Okay. Now, some other patterns that we will run into, we will find that that we can have, there's 4 possibilities when we are looking at any particular element, and that is we can have either an even number of protons and an even number of neutrons, or even odd, or odd even, or odd odd. There are 265 stable isotopes that are known, and out of that, about 3/5 of those stable isotopes have both an even number of protons and an even number of neutrons. Another fifth have an even number of protons and an odd number of neutrons. So 4/5 of all the stable isotopes are even numbered elements. It tells you we should have more even numbered elements, and that is mostly true. We have 50 of them that are an odd number of protons and an even number of neutrons, so the odd numbered elements that have an even number of neutrons. And there are exactly 5 stable isotopes that have an odd number of protons and an odd number of neutrons. And in case you're curious, they are all small. So like deuterium, which is hydrogen with a neutron, lithium 6, boron 10, what's another one? Nitrogen 14. There's one more out there, I forget. But the point is there's not very many of these, and these are all small. So pretty good bet. If you have a stable isotope, it's probably even. If you find an element that has an odd number of protons and an odd number of neutrons, it's probably unstable, unless it's one of those small ones that I just mentioned. So this is a chart. I made this chart. This chart shows the number of stable isotopes for each of the elements. So it's the number of stable isotopes for each of the elements. And you'll see here that we've got, well, there's definitely a pattern. So the ones that have 0 stable isotopes I've indicated in gray. The 2 yellow ones either have 1 or 2 stable isotopes. And the ones that are blue have 3 or more. And you'll see that some of these, there's quite a few. Like mercury, look at that. There's 7 of those for mercury. 8 for cadmium. 10, look at that, 10 for tin. For lead, there's 4. So there are a lot of stable isotopes that are those even-numbered elements. The odd-numbered elements are less likely to have as many stable isotopes, and that's just because they're not as stable. All right. The ones with asterisk indicate that one of those isotopes is a isotope with a half-life of more than 1 billion years. And so that includes one of the isotopes of potassium, potassium-40, one for thorium, and one for uranium. And actually, there's also one for bismuth. Bismuth has, well, go ahead and think it's stable. We'll just say it's stable, but technically it has a half-life that's really, really long. We'll just say that. Okay, so that's the number of stable isotopes. That's kind of a curious thing, but it reinforces that the even-numbered elements have more stable isotopes. And then finally here, we've got the elemental abundance in the galaxy. And this shows how, let me explain here. It's all normalized to silicon and 10 to the 6. So if you do log base 10 of 10 to the 6, that gives you 6. So if you come across 6, there's silicon. And so what this means, since this is a log base on the y-axis, if you go up 1 unit, that means there's 10 times as much. So silicon versus, what's right next to silicon? Aluminum. There is 10 times as much silicon in our galaxy as there is aluminum. And that's what that means. And by the way, on Earth, there's a lot of aluminum. So, okay. So there's quite a bit of that, quite a bit of silicon. So you'll see, with the exception of some of these early elements like hydrogen, hydrogen makes up about 90% of all the atoms in our galaxy. So, and then helium makes up most of the other 10%, and all the other things are kind of in the noise. So most of the mass of our galaxy is made up of these 2 things, at least most of the observable mass, which we'll save that for a later point. But the thing you'll notice here is that most of the even elements are more abundant than the odd-numbered elements directly adjacent. And let me just pick one here. We'll pick iron. Iron's nice and stable. So iron is element 26, And element 25, which is manganese, is a lot less abundant than iron. And cobalt is a lot less abundant than iron. And you'll see that all along, that most of the even-numbered elements are much more abundant than the odd-numbered elements directly adjacent to them. Now, that's not universally true. Beryllium is just not very abundant. And so lithium and boron are much more abundant than beryllium. But this is, for the most part, true across all the elements. So let's look at number 17 on the in-class assignment. So here is number 17 on that in-class assignment. I'm looking at something. Okay, so that's number 17 on our in-class assignment. And predict the type of radioactive decay of each of the following radionuclides based on the number of neutrons and protons in the nucleus. Once you've predicted the type of decay, complete and balance the nuclear reactions by filling in the missing particle. So we'll start here with oxygen. So oxygen 15. So the way that we do this is we're going to assume each of these is radioactive in one way or another. So we're going to compare that number to the average atomic mass for that element. And so here the average atomic mass for oxygen is 16. Oop, there we go. So 16, 15.999, we'll call that 16. If this number is less than the average atomic mass, that means we have too few neutrons and we're likely to undergo positron emission. So we're going to predict positron emission. All right, and so positron emission is going to be 0, +1, E, and then 15 is equal to 0 plus 15, and then 8 is equal to 1 plus 7. And element 7 is nitrogen. And that's how we do this. So that would give us positron emission. So if it's smaller, if this number is smaller than the average mass, we're going to predict positron emission, or potentially electron capture, but we're going to stick with positron emission right now. If that number is bigger than the average atomic mass, we're going to predict beta decay. And if your if your atomic number is greater than 83, we're going to predict alpha decay. So since this one has an atomic number greater than 83, we're going to predict alpha. So we got alpha decay. We'll write our alpha particle, which is 4, 2, helium. And then 222 is equal to 4 plus 218. And 86 is equal to 2 plus 84. And element 84, if we look here, there's element 84, and that is polonium, PO. Which, by the way, if you ever get a chance to get some polonium, I'm going to recommend don't. It is very, very poisonous. Okay, so here we've got tritium. So hydrogen 3. If we look, our average atomic mass for hydrogen is about 1. And we'll find that that means we have more neutrons than we would normally expect. So we're going to predict beta decay. So if the number is bigger, we'll predict beta decay. So for beta decay, we're going to get 0, -1, E. That's a beta particle, or an electron. And then 3 is equal to 0 plus 3. And 1 is equal to -1 plus 2. And element 2 is helium. So you produce some helium-3. And in case you're wondering, helium-3, that is some valuable stuff. If you get any helium-3, hold on to it. That stuff is super valuable. All right, so here we've got copper 68. We're going to compare that number. So here is copper at element 29, and it's got a mass number of 63.55. And so since this number is bigger, we're going to predict beta decay. So, and I'll write beta decay over here. So there's the beta decay. 68 is equal to 0 plus 68. And then 29 is negative 1 plus 30. And if we look here, element 30 is zinc. So there we go. That is zinc. All right. Before we finish this section, section 2, there's one little thing I want to talk about that, and that is radon. So we're going to go back to the presentation. And we're going to look at something called the nuclear disintegration series. And the reason this is important is that there is a small amount of uranium-238. And by small amount, I mean, if we dug it all up, it would be a huge amount. But uranium-238, there is some amount of uranium-238 in the Earth's crust. Well, that uranium-238 has a half-life of about 4.5 billion years. And so it's constantly decaying, but just a little bit. And so since it's constantly decaying, it's going to be constantly producing some of this stuff, which is thorium-234. And any of these blue arrows going down and to the left, those are alpha decays. So large nuclei, and we're going to just do uranium-238 as our example. They'll decay into other nuclei, other radioactive nuclei. And the ones that are alpha decay, the atomic number is going to decrease by 2, and the mass number is going to decrease by 4. And so it'll go down. And then it turns out thorium-234, it will undergo alpha decay, but the beta decay is much faster than the alpha decay of thorium-234. So thorium-234 will undergo beta decay to give us protactinium-234. And protactinium-234 will undergo beta decay to give us uranium-234. And uranium-234 undergoes alpha decay. And then we'll have another alpha, 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 all the way down to lead, beta, beta, alpha, beta, beta, alpha. And then finally, at lead-206, we have a stable isotope. So we get a series of alpha decays and beta decays. And what's interesting is that it'll usually end up with a stable isotope of lead. And in fact, if you're trying to determine how old a particular rock is, you can compare the amount of uranium-238 to the amount of lead-206, and you can get an estimate of how old that rock is. And usually it's helpful if it's in the billions of years. All right, now there's one interesting part of this, and that one interesting part is that one of these radioisotopes that's up here is a gas. So pause the video for a second and see if you can find it. Okay, I'm assuming that you found it and that gas is radon. And I'm going to go to my periodic table here. So here is radon, element 86. It is a gas. It is a very dense gas. It tends to stay in low-lying areas. So there is radon. So I'm going to go back. Radon is radioactive. It is colorless, odorless, and quite deadly. If you breathe it in, you won't notice it right away, but it will. You will get the possibility of having alpha decay inside of your lungs, and alpha decay inside your lungs is really, really bad. It increases the likelihood of getting mutations of cells in your lungs and increases the likelihood of getting cancer. And in fact, the second leading cause of lung cancer deaths in the United States comes from radon. It's about 20,000 people every year in the United States die from lung cancer caused by radon. So something to take seriously. So the radioactive gas is radon. So now, what can we do about that? Well, one of the things you can do is stay away from areas that are more likely to have radon in those areas. And you'll find that those tend to be low-lying areas like your basement. And if you do find that there's radon in your basement, you can very simply just get a fan that blows the air out of that room and puts it outside, and then that radon will seep back into the soil, and it will take much, much longer than the lifetime of you living there for it to eventually seep back in. So what you'll find is that you can effectively mitigate the problem of having radon in your basement by just blowing the air out. Pretty easy. So people who live in areas that have high concentrations of radon will periodically get it checked to make sure that they are not being exposed to radon. And whenever you buy a new house, that is something that you usually will get checked. If you have a basement. If you don't have a basement, it's really not much of a concern because it stays in the ground and you're not going into the ground. So here, this is a radon map. This map was produced by the Environmental Protection Agency, the EPA. And the EPA, they published this. The red areas have higher concentrations of radon. This is by county. So the red areas have higher concentrations of radon and therefore have higher radioactivity in the soil. They developed this in the early 90s as a way to give people a way to assess the risk and help governments and other organizations assess risk and assess resources so that they can mitigate the problem. You'll see that in the North Texas area where most of us live, that it is relatively low, but that does not guarantee that there is not radon. This is, like I said, this is done by county, and there can be locally concentrated areas of radon in the soil. Now, if you don't have a basement, it's not really an issue. So I present this page not as a learning objective, but as a public service announcement. So that seems like a good place to end our first video. So I'm going to, our next section is going to be Chapter 21, Section 3. We'll talk about nuclear transmutation. So we're going to end on the radon map.